All right, folks. We are recording now. Let's have a little.
You're recording?
Yes, I. Gosh, Brian. Yeah,
Brian Seltzer.
Captain Obvious.
Our banana got split.
You have to use ours now.
Go.
So you should remember to bring to tomorrow's test your unit circle. If you've lost your handcrafted unit circle, you could print out a nice one from the internet, and I will look the other way and say, well, you really should have your own, but we'll cut you some slack on that one. If you're always printing out a unit circle from the internet, you're always having to refamiliarize yourself with how they arranged it and how they set it up, and if there are colors, how the colors work. If you make your own, it's yours. It's like, you know, a piece of well-worn clothing that you know inside and out. Also, you can bring your 3x5 note card, but not a graphing calculator. And we'll have the scientific calculators here for you. All right, question number 1. We're going to be looking at parametric equations involving trigonometry. So we're given a system of parametric equations, a function for x and a function for y.
Pass the tardy sauce.
Oh, that's on the recording. Hi, recording.
So we want to look at these equations and ask ourselves a couple of questions. For example, what is the period for the x of t function? So looking for the period, we want to say, okay, it's a sine function, and we're looking inside the parentheses here, and we've got a b value of pi. That's a funky looking pi. There you go, it's still funky. So is that the period?
Nope.
No, it's not. So you can figure out the period for a sine function or cosine function by using this little equation. Period is equal to 2 pi divided by the b value. This is if you're in radians, which we are at this point. So our b value is pi, so 2 pi over pi is just 2. If you look at the y equation, negative 2 cosine of pi t, would use the same equation to figure out its period, and its period is also 2. For the amplitude, we're looking before the trig function, so this is a measure of its vertical stretch. The basic sine and cosine functions have an amplitude of 1 because they go to positive 1 and negative 1. So with the 3 in front, the x equation is going to go from positive 3 to negative 3. So the amplitude in that case is just 3. For the y equation, we have a negative 2 in front. So cosine again has an output of plus or minus 1. So now with that negative 2, we're going to have an output of minus or plus 2. Now you're tempted maybe to look at this and say the amplitude is negative 2, but the amplitude isn't defined as being a positive or negative value. It's always positive because we're really thinking about the distance from the midline of the function to its maximum value, and that should be a positive value. Oops, let's see. Now, we have given you a couple of aids here to help you figure out how to sketch Doodle's path on the xy plane. So again, thinking back to this, we've given you an equation for x and an equation for y. The equations are telling you where in x Doodle is for any time, and where in the y coordinate Doodle is for any time. And from those two, we're expecting you somehow magically to come up with a path on this xy grid. Is this unreasonable?
Yes.
Of course it is. Right? No, it's not. So
No.
it's totally reasonable. So here's what we're going to do to help you along with that. On part C here, we're asking you to sketch x as a function of time and y as a function of time on their own little graphs to help you visualize what's going on. So the x function is, again, 3 sine of pi t. We know the period is 2, so I'm going to put in some marks on the time scale. This is 1, this is 2. And I'm going to sketch the graph for sine of pi t. So sine starts at the origin, goes up, goes back through the t-axis at 1. This is why we can't use these recordings. People talk too much.
Wait, do we need the y?
And on the vertical axis, we have a maximum of 3 and the minimum of -3. So the expectation is that when asked, you can reproduce a basic sine function and a basic cosine function as a graph. I don't think that's too unreasonable.
Yes, it is. Does that start at 0?
Starts at 0, yes. Only my bad handwriting says otherwise. Oh. Now, for the y function, we can use the same scale for the time. Cosine starts at +1. Our function has a -2 multiplied by that. So our function is going to start at -2. And it will go through the t-axis and be maximum at 1 and go back down and return to -2 at t equals 2. Maximum value over there is 2.
Wait, so, because normally, hold up, why is y cosine and x sine?
Right. So we can use, and we will, I warn you, we can be arbitrary about what trig function we use here to indicate the horizontal position and the vertical position. So if you're thinking, and this is good, you're thinking in terms of the unit circle where the x is the cosine, the y is the sine. But for parametric equations in a path like this, we can change it up. We can say, oh, the x position is given by the sine function, or the y position is given by the cosine function. And that is confusing, which is why we're taking this extra step of graphing these functions independent of the xy plane. Just thinking about what do the functions do, and then we'll put it together on the xy plane.
And then it starts at -2 because it would normally start at 1, but it's just...
Right, so we multiplied it by -2. So we've flipped the cosine function upside down, reflected it over the t-axis. So when t is equal to 0, let's figure out where doodle is. So I'm circling the x position and the y position when t is equal to 0. And in this case, the x-coordinate is 0, and the y-coordinate is -2. And that's this point down here. So we've taken the x and y positions from the two graphs on the left, and we've translated it into a single point on the xy plane. You'll notice the xy plane has no t-axis, so we can't see what time anything is yet. But we happen to know that at this initial time, and I'll even put an arrow there with the note IP for initial point. That's where this curve starts. Now if I go to 1/2 second, the x curve is at its maximum. The y curve is on the t-axis. It's at 0. So our second point that we could graph is at x equals 3, y equals 0, which is over there. The next point I could do, I'll use a triangle symbol. The x-coordinate is 0, and the y-coordinate is 2. And which symbol should I use for the next time? Oval. Okay, oval. X-coordinate is -3, and the y-coordinate is 0. And then finally, when we get to 2 seconds, I'm going to go back to circles again. We're at the same point we were when we started. X is 0 and y is -2. So I don't need to draw that symbol again. So this point that we ended up at is the same as where we started. So we're going to refer to this as the terminal point, TP. Now, we started here. I'm going to change my color back. We started here. We know from experience this kind of parametric equation gives us an elliptical shape, because we did these in the classwork. And as I draw this path in, I'm also leaving arrowheads behind to show what direction I'm going in. All right. So finally, did I label the initial and terminal points on the path? Yes, I did. And did I show her direction of motion using an arrowhead? Yes, I did. Several, in fact. And so now we know everything we need to know about Doodle's path. Doodle starts at 0, -2. She goes counterclockwise in an elliptical path and returns after 2 seconds at her starting point. Oops, I didn't want to do that. There we go. Any questions? All right, let's move forward. All right, so these are fun. So now Doodle starts at point A and follows the closed path. What kind of hell is this where we have this Doodle thing driving around these shapes? Anyway, in a counterclockwise direction, so we have our initial point and right here going this direction, and we're landing at several points. Okay, so Doodle drives at a speed of 1 unit per second. How long does she need to complete the circuit? So we just need to count squares going around the perimeter of this shape. That's all. The bottom from A to B is 1, 2, 3 units. From B to C is 2 units. From C to D, anybody care to guess?
4, 10.
Wow.
I'm going to say 3 or 4. I'm going to say 4.
All right, maybe we shouldn't guess then. Tell you what, 4 seems fair.
Oh.
This is a right triangle. It's 3 on this side.
5.
Oh, so it's 5.
Bingo!
Well, I was 14.
I guess the whole let's guess was probably a bad idea, huh? And the final side looks like it's going to be 1, 2, 3, 4, 5, 6. So the total distance is 3 plus 2 plus 5 plus 6. And if it drives 1 unit per second, the total time required to go around is the same as the distance. So it looks like 16 to go all the way around.
16 seconds.
16 seconds.
Yeah, units, Mr. Dennis.
Units, Mr. Dennison.
She's nice.
So embarrassed. If Doodle is at point A at 0 seconds, when is she at the following points? So if Doodle is at point A at 0 seconds, when is she at B?
30 seconds.
What? How many?
3.
3. When is she at C?
5.
When is she at D?
10.
This is
11.
10. And when does she get back to A?
16.
16.
Interesting.
Seconds, 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 seconds. So you'll notice we're kind of doing this question in reverse of what we did on the first page. First page, we came up with some x as a function of time and y as a function of time graphs using trigonometry. And in this case, we're going backwards. We followed the path around, and we're recording where she is at various points in time. Now we're going to translate that into an x as a function of time graph and a y as a function of time graph. All right, so you might want to, you have the luxury of seeing the whole page at once now. When we're at time equals 0, what is Doodle's x-coordinate?
Negative 1.
-1? So I'm putting a point here. This is point A. When Doodle's at point B, what is her x-coordinate?
2.
And that's at 3 seconds. So at 3 seconds, she's at x equals 2. The next point is point C. That's at 5 seconds. What's Doodle's x-coordinate at 5 seconds?
2.
Still 2. And D is at 10 seconds. What is Doodle's coordinate then? X-coordinate?
Negative.
-1.
-1. And at 16 seconds, we're back at point A. What is Doodle's x-coordinate then? -1. Did Doodle's x-coordinate change on the way from D to A? No.
Weird spacing.
Oops.
Wait, why is C's x coordinate 5? Wouldn't it be 2?
DC. I'm actually looking at the times. So the horizontal scale here is time, and we have the times shown in this list up here. So our horizontal positions that are of interest to us are 0, 3, 5, 10, and 16. The vertical positions are the x-coordinates. This is very mind-bending. The x-coordinates give you the vertical position on this graph.
Wait. Okay, so my mind isn't taking this. So on this x graph, the x-axis represents time, and the y-axis represents the x value.
Yep.
Yeah, see, that's confusing.
See this
Okay.
legend up here? This is x. The vertical scale is x as a function of time.
Okay, so A starts out at -1, so it's 0. I get it, kind of. Okay, so we're just going by those up there. And
Yep.
then, okay.
And this is exactly the kind of graph we had on the first page. We were showing, it was labeled, it was the same idea. We have x as a function of time and y as a function of time. Here we're just building it in reverse.
And then because B's x coordinate was 2, and then add that. Okay.
Yep. All right, now we're going to look at the y coordinates. So for Doodle, what's Doodle's y coordinate when t is equal to 0?
-1.
That's point A. Doodle's y coordinate when t is equal to 3, point B.
Oh, no, okay, wait.
Also -1. Doodle's y coordinate at point C when time is equal to 5,
1.
+1. Let's see, and t equals 10. The y coordinate for Doodle is 5. It's the very top of the figure. And then finally, at 16 seconds, we're back at point A, where Doodle's position, y position, was -1. So we're back at point A, and we'll hook that up with a straight line.
Are we straight line?
These are straight line, yep. So this is unlike the previous graph that was nice and curved because the original function was generated from sine and cosine, which have nice swoopy curves. This is all determined by the shape to begin with, and you'll notice when you're going, you know, from D to A, you're moving at a constant speed. So the rate at which the y-coordinate changes is constant with respect to time, and that gives you a straight line. And now let's think a little bit about the properties of these curves. We look at the x of t function. What's the period? Well, we don't have multiple periods to look at to say, but what do you expect how many seconds will it take before this always repeats?
16.
16. What about the y of t function? Should be the same thing because we're ending up at the same point after 16 seconds on the xy grid. And amplitude. What's the amplitude of the x of t function? Well, we want to look at
Wait.
the distance from the minimum to the maximum, which is 3, and then divided by 2. So we have 1.5. And then for the y of t function, we've got a distance here of 6, and divide that by 2, which gives us an amplitude of 3. Questions so far?
Is the test going to be this short?
Probably a wee bit shorter.
What?
Speedy.
Oh.
Oh. Oh.
What are we
Anyway,
doing after this? Do we start doing review from
we got a project coming up.
You get a 72. Will's going to fail this test.
Will bother.
Yeah,
Will get-
shouldn't, no.
Way too bothered.
So, page 3, we have a periodic function, f of x, and we're going to figure out a few things about it. Shh, that's why we can't have nice things. First of all, what's the period? Period is the horizontal distance for that function to begin repeating.
6?
Six.
6. So you can literally take two features on the curve that you can identify and count the squares horizontally between them. Check to make sure that the horizontal scale doesn't have some weird number of units per square or something. This is just 1 to 1. So we have a period of 6. Amplitude. Now we're looking at this vertical height. That was pretty bad. For some reason where I put the pen and where it draws a line don't seem to be lining up too well. Still not. So the total height there is 4. And we're going to divide that by 2 to get an amplitude of 2. Now, part C. F of 4 means only that we're using this graph. 4 is the horizontal position. That's the x going into the function. F of 4 means what is the vertical position of the function when x is equal to 4. So we're going to go look at the graph on the horizontal scale when x is equal to 4, and then see where that vertical line crosses the function. And it crosses the function at a vertical position of 2. So f of 4 is 2. F of 0, we'll look at x equals 0, and it looks like the function goes right through the origin, so f of 0 is 0. This is so easy. F of 11,
So you say
that's right.
Hey, you're probably going to change it.
F of 11 is negative 1. Why do they even bother asking questions like this? It's so, wait, F of 77. All right.
-1.
Why is it negative 1?
Okay, mine's 11.
Like, I'd be 11 already, and it's just like
It's like 11, but like
Oh, because
7 times so over to the right.
Oh, I see what she's saying.
Or is that wrong?
F of 11, 7 times over. In order for this to be true,
Oh, your period would have to be 11.
what's the difference between 77 and 11?
56.
The key thing is that 66 is divisible by the period. So yeah, f of 77 is the same as f of 11 because the difference between them is a multiple of the period, 6. Now, if it hadn't been so, it would have been a little trickier. You can always divide the 77 by the period. You could say 77 divided by 6 equals, gosh, what does it equal? 12 with a remainder of 5. And in that case, you'd say, okay, well, it goes in 12 times, but it's the remainder of 5 that I'm interested in because that means that f of 5 will be equal to f of 77. And incidentally equals f of 11. And they're all going to give you, if you look up 5 on this, you'll see -1. All of those options will give you -1. So in general, things in terms of things to think about when trying to work this out, you can do this division, divide by the period, and take the remainder. And that'll be the same point in the periodic function. All right. We are going to do some transformations. This is old stuff. We've done this a long time ago, right? So we've done all these function transformations before, but we haven't necessarily done them with periodic functions, which is why we're doing them here. So f of x minus 2. The minus 2 is on the outside. Remember what comes out of f of x. The value of f of x is a vertical position. So f of x minus 2 means we're taking its vertical position and we're subtracting 2. In terms of the graph, it means you're going to draw the same graph as the parent function, but 2 units lower on the grid. So, way to do this is to identify the key points on the original curve and draw them 2 units lower. So this first one that I circled up here, I'm just drawing it down here. So this point here on this graph would be here, but I'm going to draw it 2 units lower. This next point up here is at y equals 3, but I'm going to draw it at y equals 1. And then the next point, you can go relative to the last point. I could say this one is 3 units to the right and 1 unit lower. So on my lower graph, I'll go 3 units to the right and 1 unit lower. And then the next point is 1 unit to the right and 3 lower.
We could draw all of the little things.
Yeah, wait, do we have to do all of them, or do we just have to have it repeated once?
That's
This
not too
one
hard.
period, or all of them.
You can do all of
Why
them.
is it
Okay.
to the right and lower? Because isn't it just one?
So we can starting from this point up here, we're going 3 to the right and 1 down, 1 to the right and 3 down,
What?
and then 2 to the right and 4 up. Or if you're drawing features, you could say, well, okay, starting here, I'm going 3 to the right and 1 down, 3 to the right and 1 up, 3 to the right and 1 down, 3 to the right and 1 up, 3 to the right and 1 down. So you could draw all of those sort of in a sequence. Being, whoops.
Oh,
Being-
but you're still at the same place. You're just 2 down.
Yep.
Okay, I thought that was like you were doing the transformation.
So this is just,
So just down 2.
and then I can hook them together. So that was down 2 units.
Oh, now it's just down 1.
Not quite.
Oh,
We
2.
we have to do 2 things in
Oh,
sequence.
no.
So our order of operations says that we take whatever comes out of the function and we multiply it by 2 first, then down 1. So I can just barely put these 2 in the same screen at the same time. So like starting with this one that I circled before, at x equals -7, that original value was y of -1, so multiply that by 2, we'll get -2, and then we drop it 1, we'll be at -3. Or if I look at this point up here, which was at -8,2, if I multiply that by 2 by -8,4, then subtract 1 will be -8,3. Now, remember on this last curve, I sort of went across going over 3 down 1, over 3 up 1, over 3 down 1, over 3 up 1. Because the vertical stretch is 2, I can do the same thing, but it'll be over 3 down 2, over 3 up through, over 3 down 2, over 3 up 2. So I can go over 3, up 2, over 3, down 2, over 3, up 2, over 3, down 2, and just walk along. Just like that. And this point that's at the bottom here, that point is the one that repeats every 6 units. So all I need to do is walk over 6 units at a time. And I've got the whole set. And I can hook those up. Easy, right?
Yeah.
A lot.
Ooh, there's more.
It's just like
Busy work?
But easy points, so it's good.
I shouldn't say that because I'm not saying that was lost.
Okay. So the next one, f of 1/2 x. What kind of a transformation is that? Horizontal.
Stretch.
Because it's
Value
opposite.
Yeah.
Stretch horizontally by a factor of 2. Very nice. So
Oh, wait,
if you go back to your original curve, let's go back and look at a point, this one right here. This is the one, choose a point close to the y-axis first because the number is going to be the smallest. The x value is the smallest. So when x is -1, y is -1. Now for this transformation, the y's don't change, but the x's do. The x's get multiplied by 2. So this x will now become -2, and the y will be -1. And likewise, there was a point at x equals +1, at y equals 3, that goes to x equals 2. And we had a point at x equals 4 and y equals 2, so that becomes x equals 8. +2. All right, now you remember in the last one I was going over 3 down 1, or over 3 down 2, and over 3 up 2, that kind of thing. I can do the same thing here, only now I'm going over 6 down 1, over 6 up 1. So I can put in the other points. Everything is stretched out by a factor of 2. The period is not 6 anymore, the period is 12. So for my bottom points, I can go over by 12 units at a time. And so we get something that looks like this. You'll notice the original function goes through the origin. Your transformed function still goes through the origin because the x-coordinate is 0. Multiply 0 by 0, or 0 by 2, and you get 0 still. So this point did not move.
He's recording.
Finally, f of x plus 3, what's the transformation? 3 to the left. Ding, ding, ding.
Math is so tricky.
So what was at x equals -1, y equals -1, now is x equals -3, y equals -1. The one that was at x equals 1, positive 3 is now x equals -2, positive 3. And there's been no stretching, so I can do my old trick of just walking over and putting in the peaks. And with my period of 6, that hasn't changed. So I can just move along in units of 6 and drop in these negative peaks. And hook them all together. There you go. Moving on. Change the red to make this a little more visible. So I'm just going to highlight the whoops, boy, I wish my pen would register better. This is the x-axis and the y-axis. Sheesh, having a hard time with that. So first point, we're going to locate these points on the grid. First one is a radius of 3, that's the third ring out, at an angle of 60 degrees. These radials are in 15-degree increments, so the 60-degree line is here. We're at 1, 2, 3. There's our point A. Point B is the 135-degree radial. That's over here. Now, the radius is -2. So that means starting at this 135-degree radial, I actually want to measure the radius on the other side. So there's -2 at 135 degrees. It's on the other side of the origin. For C, we're going to go to -30 degrees, which is down there, and the radius is 4. So that's the fourth ring. 1, 2, 3, 4. I'm right on it. Let's see. And finally for D, we'll go to the 330-degree radial, which, lo and behold, is the same one because this is 270, 300, 330. But we've got a negative radius, so that means we're going to walk over here to the 3 ring.
Couldn't you just do -3 and then go around 330 degrees? Is that, like, would that just get you to the same answer?
Let's see. Say it again.
Couldn't you just go -3 and then go around 330 degrees?
Yep.
Okay.
Yep. So you could start by going over here, saying, oh, I'm at -3, and I'm going to walk counterclockwise 330 degrees. Same place. Absolutely.
Mr. Dempsey?
Yep.
Why is C all the way over there and not in the second quadrant of like?
Because the angle is -30. So for that one, we're measuring the angle here, clockwise from the x-axis. The radius is positive, so we don't have to flip to the other side. So you can always have a negative angle. We just have to be able to deal with that correctly. Okay, next up we have some conversions. We have a rectangular point, x and y, to -4. We're going to convert to polar.
No.
So we need a radius.
He was throwing food on our desk.
Yeah, no surprise.
Look at all this.
Outrageous.
What's happening?
So the radius, there are some things you should either remember or have in your note card. The radius is equal to the square root of x squared plus y squared. That's Pythagoras. And we have those numbers. So we have the square root of 2 squared plus 4 squared equals root 20 equals 2 root 5. The angle, we can think about where this is. 2, -4 is down in the 4th quadrant. So if we use the inverse tangent of y over x, let's see how that works out. The y is -4, x is 2. So the inverse tangent of -2, if you do ask your calculator to give you the inverse tangent of -2, it will give you a negative angle. It will give you -63.4 degrees. And that actually is the angle you want. So anytime you do an inverse trig function, you have to be careful and think about, am I getting the angle that really makes sense for this problem? In this case, we are. We should be getting something in the 4th quadrant. And a -63.4 degrees is just what we're looking for. Francesca?
So when you calculated the R value, do you have to put it in square root form or can you get a decimal? With the 2 root 5, can you simplify it to like 4.47?
You could, yeah.
Here?
If I don't say I want exact form or something like that,
Wait,
you could do that.
Why do you do 2 root 5?
That's what you get from simplifying that radical, because the square root of 20 is the square root of 4 times 5. And 4 is a perfect square, so you can bring that out.
Wait, how did you get 63? You said you did something different with calculator.
Inverse tangent of -2.
But I,
You might be in radian mode,
oh, yeah.
which would be acceptable.
Okay.
You would accept all your math.
Uh-huh. You should know which mode you're in, though.
Yeah.
And if you do this calculation in radian mode, don't put a little degree symbol on it.
Mm-hmm. Okay.
So just know what you're in. Part B is very straightforward. Part A doesn't specify whether degrees or radians. You'll notice at the top of this page we're dealing in degrees. I'm sorry. So it would be acceptable here to give an answer either way. In Part B, the angle is given to you in degrees, so you had better be in degree mode or your calculation won't work at all. X is equal to r cosine of theta. You should know that in your sleep. Y is equal to r sine of theta. So all we're doing is plugging in 3 times cosine of 100 degrees, 3 times the sine of 100 degrees. And there isn't actually any thinking to do about this. And then you express express it as a point. So the x-coordinate goes first, obviously. And you write it as a pair. Now, hey, we're going to fit this in. You're thinking, you look at the last question and say, this is going to take forever, right? Yep, okay. So sine of theta is y over r. Cosine of theta is x over r. So I'll rewrite this. Again, so what I'm trying to do is get this into rectangular form, just x's and y's. I'm going to start by going to just y's and x's and r's and see what happens. So I'm going to rewrite this equation. R equals 3 over y over r plus x over r. It's a little thing down there. Now, these two fractions that I'm adding have a common denominator, lucky me. So that becomes y plus x over r. And that becomes 3r over y plus x. Why did I do that? I'm multiplying by the reciprocal of, yeah. Whenever you've got something scary in your denominator, multiply by its reciprocal. And now, looking at this equation as a whole, I've got r equals 3r over y plus x. And that means I can divide by r on both sides. You get 1 equals 3 over y plus x. Or x plus y equals 3. All x's, all y's, no r's, no thetas. I'm done. All right? Have a great day, folks. See you tomorrow.
Thank you, Mr. Dixon.